Welcome back to Honey of Knowledge. Let's continue with our discussion on linear regression. And in this lecture of econometrics, we will be talking about multiple linear regression. Multiple linear regression is simply an expansion of our basic golden econometric equation in which we had just one explanatory variable or just one independent variable. We have many names for that. We sometimes call it predictor and things like those. But that's not that important right now. The important thing here is in place of just one predictor or one independent variable, we will be having more number of such variables. So in place of y is equal to a plus bx plus e, where x is your independent variable, we will be moving on to a model in which we have y is equal to a plus bx plus cz plus e. Now in this model we are having two independent variables x and z. We can also have more. We can take x, z, w, x, z, w, k. I mean, you can have as many as you like. That's why the name is multiple. So multiple means more number of independent variables. Linear regression means that the equation of the model is linear, and linear in the sense that my independent variables are linearly combined. I have x to the power 1, z to the power 1. So this is the basic introduction to multiple linear regression model. Now this is the most basic of the multiple linear regression models, only with two variables, as this was the simplest of linear regression models with just one independent variable. So we will be expanding onto this golden econometric equation. Let's jump into the maths of it. We'll be doing all the math for a case where we have just two independent variables x and z. Just for the sake of simplicity, it can be readily expanded to more number of independent variables, 2, 3, 4, as many as you like. So just to make the things clear and tenable, we are taking 2. So what is the data in this kind of a model? You have a set of points y, x, z, and depending on the number of points n, you will be having the data for. So you will be having, let's say n is 50. So you will be having 50 such points, y1, x1, z1, y2, x2, z2, and so on till 50, y50, x50, z50. So this is your data. Now once you have this data, y is the variable which you want to predict, and x and z are your predictors. So you can put in the model in such a way that x and z are to one side, as we just saw before. So if we plug this thing in the model, you will get, and this I varies for all I equals to 1 to n. Now over here we know that EI is the error, and we want to reduce this or minimize this. So minimizing the error or residual is the main task of this mathematical exercise. So let's just collect all the terms to one side to understand the error term. So EI will be equal to YI minus A plus BXI plus CZI. Now over here, as we have done before for the linear regression, in which we just had one predictor or one independent variable, we would be not doing any analysis with this, but we will be doing error square or residual square. So we will have all positive numbers, and once we have all positive numbers, we are safe because we are not running a risk of cancelling out the errors. So we will be having a kind of data which is all positive numbers, and we want to minimize them. So next task is to set up a minimization of this thing. To be more precise, our task is to minimize. And if you just recall our previous lectures, we need to differentiate this and get normal equations. So let's differentiate with respect to A, B and C, because these are the parameters we are trying to estimate based on this least square estimation principle. Differentiating it with respect to A, we will get, and we have to put this equal to 0. Now let's differentiate it with respect to B. Over here we had an extra xi term because the coefficient of B is xi here. And similarly, if we differentiate it with respect to C, we will get the same thing and we will have a zi in place of xi. So let's just write that thing down. Hence, these are your normal equations. We can just collect the terms and arrange them in a neat order. So let's just do that for the sake of it. So these are your normal equations. You can solve these equations to get the estimated values of A, B and C, and you can call them A hat, B hat, C hat. So if you solve them, you will get A hat, B hat and C hat. Now over here, this is quite easy, but the moment I get 4 variables, 5 variables and so on, solving those equations is not a very good task. It's quite tedious in nature. So we will not be handling those kind of problems in this lecture, or for that matter any practical discourse of econometrics. Those things are done by computers. So we will be just understanding what's the essence of it. So the essence here is we will get a system of linear equations and we'll solve them to get the estimated values of A hat, B hat and C hat. Once you get the values for A hat, B hat and C hat, the estimated values of ABC, you can get Y hat too. Y hat would be equal to A hat plus B hat X plus C hat Z. And if we know y hat, we can express y hat in terms of y, or rather y in terms of y hat. Y will be equal to y hat plus e hat. And I'm pretty sure you know where we are headed towards. We'll be calculating the variance here. Variance of y will be equal to variance of y hat plus variance of e hat, and the reason we are omitting the covariance of y hat and e hat is because we have already discussed this in the previous lecture, that covariance of y hat and e hat is going to be 0. So now let's divide whole throughout by variance of y. And you can recall that this quantity, this guy over here, is the proportion of variance explained by the model, and this is the unexplained proportion of variation. So this guy over here, if you recall, is going to be your coefficient of determination, or R square. So let's just write this thing down again neatly. And coefficient of determination R square over here in this particular model can also be written as equal to correlation coefficient or multiple correlation coefficient between y and y hat whole square. Coefficient of determination R square can also be written as the square of correlation coefficient between y and y hat. Mind you, this is not between any independent variable and dependent one. It is between y hat and y. In the simple linear regression model, we did the same kind of analysis but with y and x. Over here there is no x, we have x and z both. So rather than taking just x or z, we are taking y hat, because that is what we are making the correlation on. And as we know, this must be high for a model to be good. So a 90% of R square is better than a 60% of R square, because the idea remains the same. This is the explanatory power of the model. There is yet another way to look at multiple correlation coefficient. If we set up an exercise of finding the multiple correlation coefficient between y and a plus bx plus cz by changing the values of a, b and c. So essentially you are trying to change the values of a, b, c to get different values of a plus bx plus cz, and then you're finding the multiple correlation coefficient, and then if you square it and then find the maximum for this variable, you will get the same least square estimates a hat, b hat and c hat. I'll just try to make it more clear to you. If you try to find the maximum of multiple correlation coefficient to the power 2 or square of the multiple correlation coefficient by changing a, b, c values, you will get a hat, b hat, c hat, the same least square estimates of a, b and c. So in effect, least square estimation which we did earlier, which is minimization of sum of the residual squares, is the same as this maximization of multiple correlation coefficient square between y and a plus bx plus cz. Now next thing over here is, you might have thought about that r square is high, so the model is good. But let me tell you something more. There's a property that if you keep on increasing the independent variables or the explanatory variables, R square increases, coefficient of determination increases. So this property of R square, that it never falls down when you add more variables into it as explanatory variables, gives you an illusion. If you keep on adding more variables, it will be better for you, and you can compare two models having different number of explanatory variables, which is not true, because it might happen that one model which has just one explanatory variable could have a good amount of R square, and a different model which has high R square, higher than the earlier model, just on account of more number of variables, is not a good model. So if you want to have a good model, you need to find out a way to evade this property, because R square will keep on increasing or not decrease if you keep on adding variables. Either it will stay there or it will increase, it will never decrease. So to counter this, we need to penalize the addition of new variables or new explanatory variables. See, over here we need to be careful. Why we are doing multiple linear regression? Because it's always better to have more explanatory variables, because you can finally understand which variables are getting into the model and improving the model, and then you can weed out the variables which you don't need. But just blindly adding variables and thinking it will be a good model is a foolish idea. So over here we need to find out a way to penalize the addition of explanatory variables, and that way is adjusted R squared. So adjusted R squared is a way to get the value of coefficient of determination adjusted for the number of explanatory variables. Let's look at the formula for adjusted R square. Adjusted R square or R square bar is equal to 1 minus this quantity, and this quantity is 1 minus R square multiplied by n minus 1 upon n minus k minus 1. N is the number of data points. N is the number of data points. And K is the number of explanatory variables or number of independent variables. So K is the number of independent variables. If you have the simple model in which you have just one independent variable or one explanatory variable, k would be 1, and the moment you get k equal to 1, this will be n minus 1 minus 1 or n minus 2. That is why adjusted R square is slightly lower than R square in most of the cases. Adjusted R square can also become negative. So that is one key difference between r square and adjusted r square, that r square can never be negative because it's either a correlation coefficient or multiple correlation coefficient. But adjusted r square, just on the account of this kind of modified subtraction, can become negative. But this is a good way to understand which model is better when you have different models with different explanatory variables, one with 2, one with 3, one with 1, one with 4. So you need to find out which model is good. So then we calculate the adjusted R square. Most of the packages in Python, R, Stata and other programming languages or statistical programming languages have a tool to calculate adjusted R square. So you don't need to be worried about calculating this value. But yes, if you want to calculate it, this is the formula. And this is a way to penalize R square to get the adjusted effect on R square based on the explanatory variables. What if you have this kind of a model? This certainly is not a linear model, but can you do regression on this? It turns out yes. Let's take logarithm on both the sides. If you do that, you will get log y is equal to log a plus b log x plus c log z plus log e. If you look at this equation carefully, log y is going to be your predicted variable, and this predicted variable is dependent on log x and log z, and that too in a linear way. And coefficient of log x is b and coefficient of log z is c, and this thing over here is your residual or error. And over here, if you just replace log y to be some y star, you will have y star is equal to, and you can take log a to be some a star. This will be your a star plus, take log x as x star, you will have b x star, and then take log z as z star, you will have plus c z star, and take log e as some e star, you will get e star over here. And if you look at this equation, this is your simple multiple linear regression model. So it turns out that you can try to find out ways to use multiple linear regression in more ways than you think. So this is a pretty powerful result, and you need to be careful with this kind of an exercise, because generally if you go ahead on a statistical software, you might commit a kind of an error, because all the packages will give you the summary statistics report based on y star and not y values, and you need to finally reconcile this y star with y. So that is a kind of an application part of this, which is beyond the scope of this lecture. Maybe I'll cover it in a different lecture on Python, on R or other statistical softwares. With this, the lecture on multiple linear regression, the introduction part of this lecture, is over, and we will be moving to a more advanced version of econometrics where we will be using linear algebra. But before the linear algebra part of econometric analysis, I'll be also doing something called partial correlation coefficient. So the next lecture will be a very brief video on partial correlation coefficient, because that I feel is an independent topic in itself, and I don't want to club it with this lecture or the next lecture. So after this lecture, we will be having a lecture on partial correlation coefficient. Thank you for watching this video. I hope you had learned something today, and if you liked it and learned something today, please give it a thumbs up, and don't forget to subscribe to this channel for more econometrics and more economics and maths ideas, lectures and concepts. Thank you.